Hey guys, today we are talking about the ideal gas law. So far we've talked about all the gas laws. We did Boyle's, Charles, Gay-Lussac's combined gas law, and today we're learning about the last one, which is the ideal gas law. So let's go ahead and jump into it. So what is the ideal gas law? So this compares the current conditions of our gas to standard conditions, also known as R. So the equation that we're going to be taking a look at today is PV is equal to nRT. Okay, so this will be the equation that we are using to solve our problems today. Now, standard conditions for a gas are in this yellow box. Okay, I would write these in your notes, keep them with you. We should have written them. I know the standard temperature and atmosphere from yesterday's lesson, but you do need to know all of these and keep them with you for your quiz. And for your final exam that's coming up. So for standard conditions, the pressure is 1 atmosphere or 101.3 kilopascals or 760 torr. Right? These are all the same thing. They're just different measurements of pressure, so different standards of pressure, units of pressure. So atmosphere, kilopascals, and torr. Now volume is in liters. N is equal to your moles, so at standard pressure it's 1 mole. And then temperature is always in Kelvin. Remember, standard temperature is 273 Kelvin. Okay, so we can use these standards to compare our gas to standard conditions versus whatever kind of state it's in currently. So when we're using this formula, R is found by plugging the standard pressure, volume, temperature, and mole values into one side of the combined gas law. Okay, so remember that combined gas law from yesterday's lesson. You'll select the appropriate R value based on the pressure unit. Okay, so what we mean by that is that the pressure is really the only one that changes units, right? Because volume's in liters, N is mole, and temperature is Kelvin. But those pressures can be in atmospheres, kilopascals, or torrs. So depending on what unit you're using, you're going to have a different R value. So if we rearrange that equation, right, R is equal to PV over NT. So if we just plug in our different pressure at standard, depending on the unit, these are going to be the R values we come up with. So if we use the atmospheres, we would get an R value of 0.0821 liters times atmosphere over moles Kelvin. If we use our kilopascals, if we just plug that in, we get a value of 8.314. And if we use our torrs, we get 62.36 liters times torr over moles per Kelvin. Okay, and again, it's highlighted in this kind of aqua color here to show us that we're just plugging in these different units. Okay, again, these are all at standard pressure. It just depends on the unit that the problem is telling you, right? So it could be in atmospheres, kilopascals, or in torrs. So let's take a look at a problem. So it says a 0.68 mole sample of carbon dioxide gas has a pressure of 2.5 atmospheres and a temperature of 30 degrees Celsius. What is the volume of the gas, and how do these conditions compare to our standard? So let's go ahead and plug this in. So our equation, again, is PV equals nRT. Our 0.68 is our N value, so it's our mole, so we know we're going to put the 0.68 here. 2.5 atm, that's our pressure, so that will go here. 30 degrees Celsius is going to be our temperature, that will go here, but remember we've got to convert it to Kelvin, so we'll do 30 plus 273 to get our Kelvin. And then we are looking for the volume. Okay, so we're looking for the blue. So we have our pressure, we have our moles, we have our T, our temperature, which we just have to convert to Kelvin. Then we have to find our R value. We have to use it based on our unit of our pressure, which in this case was atmosphere. So we're going to use that first value from that previous slide. Okay, so if we rearrange to solve, we're going to find that our volume is equal to nRT over P, okay? And the way that we got this, we want to isolate the V, so we're just dividing by the pressure on each side, and then we can plug and chug, right? So we're going to do 0.68 moles times 0.0821 liters times atmosphere over moles Kelvin. And again, this value, we know it's on the previous slide, right? So that slide before where we did all those calculations. And we know because the pressure is in atmospheres, we're using that first one because we're using it with the standard temperature and pressure at 1 atm. Then 303 Kelvin, again, that's from adding 273 to 30, all divided by those atmospheres, which is 2.5, okay? So our volume is 6.77 liters, okay? So our volume is 6.77 liters. So if we compare that to our standard conditions, our sample has fewer particles, takes up less space, so the volume is lower, it has more thermal energy, and is colliding more in its container, right? So we're basically just comparing it to standard temperature and pressure, right? So like for example, the temperature is 30 degrees Celsius, which is 303 Kelvin. That's higher than 273, so we can infer that this gas has a higher temperature, and because it has a higher temperature, it has more thermal energy, okay? Also, the volume is 6.77 liters, which takes up less space, okay? And then the pressure is also lower. So our pressure is, in this particular problem, it tells us our pressure is 2.5 atm, which is higher than our original pressure of 1 atmosphere, okay? So these numbers we're comparing to standard pressure and standard atmosphere, standard conditions, which are what was in that yellow box at the beginning, okay? And then here's just a way to visualize that as well. So here's our standard conditions. And then in our problem that we just solved, we had a smaller volume, right, because standard is 22.4 liters, and we came up with a little over 6 liters. So smaller volume means less space for these molecules to collide, fewer particles overall. We had a higher temperature, which meant there's more kinetic energy, so these particles are moving faster. And then they had higher pressure, which means there's more collisions overall, okay? So again, when we're using this ideal gas law, we are just comparing our new conditions to standard conditions, okay? Now there are some more examples on here. I'm not going to go through all of them because you guys have access to them on the slides, but I would encourage you to go and work through them and just take a look at these slides yourself and see how all these things plug in and work out. But other than that, that is it. So if you guys have any questions, definitely let me know. I know that there have been a lot of equations that we've learned this week and a lot of different applications. But if you have any questions, I will be more than willing to hop on and help you guys answer those. So you guys are good to move on to your assignment today if you don't have any questions, and I will catch you guys next time. Bye, guys.